before we learn a different way to represent electron configurations, we're going to learn a shortcut for writing electron configurations, especially for those elements that have a very large number of electrons. To understand how the shortcut works, let's take a look at the electron configurations for fluorine, its ion fluoride, sodium, its ion sodium with a positive 1 charge, and neon. If we take a look at the electron configurations for fluoride, positively charged sodium, and neon, we see that they are identical, meaning that they not only have the same number of electrons, but that those electrons are at the same energy levels and at the same subshells. Now, things get more interesting when we compare the Lewis structures of all of these elements and ions here. We know that fluorine starts with 7 valence electrons, and remember that Lewis structures only show the outermost electrons in the valence shell. And in order fluorine to become a stable ion, it needs to gain 1 additional electron for a total of 8. We know that sodium starts with 1 valence electron, which it has to lose in order to have a full valence shell. And again, the Lewis structure has 0 valence electrons, although remember, a stable valence shell always has 8 valence electrons, and when sodium loses its outermost electron, the electrons underneath become the new valence shell, which is why we can also say that sodium has a stable 8 valence electrons. Neon is a noble gas, so we know that it has 8 valence electrons, which is why it starts out as being stable and why it doesn't react. Now, again, we see that the 3 ions and elements, fluoride, sodium plus 1, and neon, which have the same electron configuration, also have the same number of valence electrons. It is for this reason why this shortcut is possible. So we can write an element's electron configuration in a short form that we call core notation, which separates an element's electrons into 2 groups. There are the core electrons on the inside and the valence electrons on the outermost layer. And the core electrons, because they are underneath the valence electrons, do not get involved in the chemical reaction in the same way that neon's electrons, because neon is a noble gas, are not involved because its valence shell is full. In order to explain how core notation works, it's always easiest if we try a few examples to represent this. So the first thing that we're going to do is write out the electron configurations for 3 different elements. So if we check our periodic table, here is oxygen. So we know that oxygen is element number 8. Then we're going to take a look at phosphorus, and then we're going to take a look at calcium. So if we write out the electron configuration for oxygen, we start at energy level 1, 1s, 1, 2, 2s, 1, 2, 2p, 1, 2, 3, 4. So let's go back and write that in. 1s2, 2s2, 2p4, and we know if we count the total number of electrons, oxygen has 8 electrons, and on the periodic table it is element number 8. So now let's do the same thing for phosphorus. So here's phosphorus, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. So let's go and write that configuration down. 1s2, 2s2, 2p6, 3s2, 3p3, and finally for calcium, same idea. 1s2, 2s2, 2p6, 3s2, 3p6, 4s, 1, 2. So let's rewrite that configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, how do we identify which electrons are the core electrons and which electrons are the valence electrons? Well, in each element's case, we need to go back to the periodic table and we need to look for the closest noble gas that is smaller than the element we're describing. So if we do this for oxygen, we can't use neon because neon has more electrons than oxygen and therefore it's a bigger element with a higher atomic number. So we actually need to go all the way back up to helium. So helium is the closest noble gas to oxygen that isn't larger than oxygen. If we do this for phosphorus, we can't use argon, so we have to go all the way back to neon. So neon is the closest noble gas to phosphorus that isn't larger. Likewise with calcium, we can't use krypton because that's a bigger element, higher atomic number, so we need to go back and we find that argon is the closest noble gas to calcium that isn't bigger. Now, the other thing that we need to remember is that each noble gas also has an electron configuration. So we know that helium's electron configuration is 1s2. It has 2 electrons and both of them are in the 1s subshell. Neon is 1s2, 2s2, 2p6, because it has 10 electrons, 2 in the first s subshell, 2 in the second, and 6 in the 2p subshell. Argon would have a longer configuration, so argon would be 1s2, 2s2, 2p6, 3s2, 3p6, because again, all of the 1s, 2s, 2p, 3s, and 3p subshells are all completely full. Now, this is important. The noble gas electron configurations are important when we go back and look at the elements that we want to shorten. So if we remember that helium, it has the electron configuration 1s2, we can put the noble gas in brackets here so that helium again represents the electrons in the 1s subshell, and then the rest of the electrons, 2s2, 2p4, in oxygen's case, we write out. So again, the noble gas here represents the core electrons. These are the ones underneath the valence shell, and the 2s2, 2p4, these are the valence electrons because they're on the outside. Now we remember, if you use your periodic table, you remember that oxygen has 6 valence electrons, and if we look at our valence electrons here, 2s2, 2p4, 6, it matches the Lewis structure, so this is no accident. Now let's do the same with phosphorus. We remember that the closest noble gas to phosphorus is neon, which is again 1s2, 2s2, 2p6, so we can use neon as the noble gas to represent 1s2, 2s2, 2p6, and all of the remaining electrons are the valence shell, 3s2, 3p3, and again we can compare this to phosphorus's Lewis structure, which has 1, 2, 3, 4, 5 valence electrons. 2 plus 3 is 5, which means the Lewis structure matches what we expected to see. Then if we do the same thing with calcium, we remember that argon, which is a much larger noble gas, is 1s2, 2s2, 2p6, 3s2, 3p6. All of those are the core electrons, so let's put argon in brackets here, and again, argon represents all the electrons from 1s2, 2s2, 2p6, 3s2, 3p6, and then only the outside 2 electrons here, 4s2, represent calcium's valence electrons. If we compare this to the Lewis structure, we know calcium has 2 valence electrons, which matches, so we're good. This is the usefulness of using core notation, because we can distinguish between the unreactive core electrons and the reactive valence electrons on the outermost layer, and that not only is easier to write and takes less time to write, it also explains why the Lewis structures are the way they are and how we can predictably determine the number of valence electrons. One final thought, if we take a look at elements that actually have d electrons here, if we follow this rule about valence electrons, that would technically mean that bromine and iodine actually have 17 valence electrons here, but we know if we draw the Lewis structures, we would draw them exactly like chlorine and fluorine, where each of them have 7 valence electrons. So what are we doing here? Now, if we think about what energy levels mean, the idea that an energy level represents how far away electrons are from the nucleus. We know that 4s and 4p are at a higher energy level than 3d because energy level 4 is bigger than energy level 3. So these valence electrons are farther away from the nucleus, which means that these electrons would be lost first if they were to be removed. Therefore, what we can do is we can actually say, because the d subshell electrons are at a lower energy level, for the purpose of counting valence electrons, we can effectively ignore this d subshell and count only electrons that are part of the s and p subshells. Therefore, bromine and iodine actually have 7 valence electrons, and d subshell electrons are not considered part of the valence shell if the d subshell is full. And using that, again, this doesn't change the way that we write core notation, still follow the noble gas rule, and everything beyond that is technically part of the valence shell, but in terms of counting which electrons are gained or lost, we ignore any electrons that are part of a full d subshell. In the next video, we are going to take this idea and look at a different way to represent electron configurations so that if you're still not sure what an energy level and what a subshell is, that will help visualize.